Welcome to the Pentair's presentation on advanced electrical motors and controls. Give you a real quick forewarning. We are going to do a quick review of single-phase motor testing, and then we'll get right into the three-phase motor testing, which is the heart of the subject today. My name is Dan Featherstone. I'm with the Pentair Training Institute. So let's go ahead and get started here. With everything, we always start our webinars. We like to go over other opportunities for you. Any of our websites, if you go to the Resource Centers tab, there on the left-hand side, if you scroll down, you'll see training opportunities, where you'll learn about the different things we offer. For example, you're probably watching this on the Pentair Learning Center, and you'll know that it's an interactive. Modules are out there. Our webinars are out there. It's a study at your own pace, and there's no charge for this, of course. You can also follow us on Facebook if you like. That gives you updates of what we're doing and different events and such. We also have a dealer reward program that we want to make sure you're aware of, especially because it gives you labor and extended warranty agreements. Not only can you just buy different merchandise on there, there is very good benefits that you want to look into this. So give it a look out at www.pentairprodealer.com. Next, we have our Pentair portal. These are for our distributors and such. Gives you 24/7 access to product availability, pricing, etc. Give Miss Amy a call at 866-880-3771. She'll be more than happy to help you. Of course, last but not least, the good old factory schools. We do offer them in the spring and in the fall. They are hands-on labs often involved with these, especially when you come to Delavan. We don't like to let you sit for long. We like to keep you moving and interactive with the equipment. Plus, there's, of course, in Delavan, there's the factory school, which a lot of guys like. For more information, like I say, go out to our website. You can sign up. Definitely worth the investment. Thank you. To get started, we're going to go ahead and first talk about single phase. Single phase 115, it's just your standard wave form here as shown. Basically one hot leg carries the bulk of the amp load. Then you go to single phase 230. Now you have, as it's shown here, the two sine waves, kind of like a two-cylinder engine, is how I describe it. Is that single phase 115 is one piston doing all the work. When you go to 230 volt single phase, now you have two pistons firing opposite each other. So that's the ideal circumstance. Gives you less amp load, smaller wire size if you have a longer wire run. Any motor, I don't care what it is, they always start out by being stamped out out of the sheet metal. They start with the stator and the rotor being stamped out in one piece. Okay, what they do now is you're going to take that stator laminate and you stack them. And the more stacks you have, the more horsepower you have, the larger magnetic coil you'll have. So as you see here, we're going to stack them to our horsepower desired. And understand each one of these laminates is roughly about a 32nd in thickness or so. And so they'll stack these to the designated horsepower. They'll then press in the copper windings, as shown here. That creates a magnetic field, which is going to turn the rotor. The rotor now, again, is made of laminates, but they're cocked. They're offset a bit, because if they're perfectly straight, when you try to fire up that in a magnetic field, the rotor would just hum. It would not spin properly. So as we stack them up, and they stack them up equal to the number of laminates in the stator, again, as long as needed for the horsepower desired. So you'll stack them, and then you'll shoot your aluminum core in there, and then while it's still hot, you press your shaft in there, which turns the pump or whatever it's going to be connected to. In our case, of course, it's the pump, but these electric motors are used everywhere, you know that. You then put on your bearings and your fan, and then that whole assembly goes together just like that. This is true for three-phase and single phase. It's no real big difference. Other than, again, like I say, the length or the number of laminates stacked will determine your horsepower. The more laminates, the more of a magnetic field they have to push the rotor. And as you see here, here's an internal picture of that stator. The stator, when pressed in, should be nice shiny copper. You see the strings tying it off, and all the insulation is in place. Okay. Now with single phase motors, you have a capacitor. See, three phase is unique in that you have three unique phases firing, and they can break the magnetic field and start the rotor to spin. For single phase, you need a capacitor. So the capacitor's sole purpose is it conducts current, pushes it through, and as you see there, that's the path. It basically is a start battery. It kicks the motor on and then cuts right out. It's not used again. Okay. Now the two yellow wires, one goes to the overload, one goes to the motor, and then of course the other side to the start switch. A capacitor, when it's black or brown in color, that's going to be your start capacitor. It's not designed to be a run capacitor. They will boil off if you do try to run them as a run phase. So be cautious of that. Now, to test it, I'll tell you, and if you've had my meter course, I'll explain this again. There's no excuse for not to be checking this stuff anymore. A good multimeter, the one like I have here shown, I can get that at Amazon.com, for example, for about $150. So, and that meter does microfarad, it does capacitance, it does mega ohm measurements, ohm measurements, it does all of it. So this start capacitor here that we're testing, one thing is to point out real quick that it's always plus 20%, but it's never lower. It can't be minus anything. As well, if you see buildup or if there's leakage from the capacitor is done. Now the other thing I want to point out too real quick is on that top picture, remember if you have a resistor in place, and all that resistor does in a capacitor is allow it to drain once the power is turned off to put it into safe mode, so to speak. You got to cut that out in order to get the proper measurement. If you choose, you can solder it back in place, but like I say, the only thing that resistor does is drain the capacitor, which you can achieve, and what you should always do is when you turn off any electric motor or control box and de-energize it, if you're going to touch the capacitor, remember use an insulated screwdriver, go across the points to discharge it, even if there's a resistor. Always be safe in handling capacitors. This is the old test where you watch the meter swing with the Simpson. Don't bother with it. It only tells you that the capacitor is able to see a charge and grab it. It doesn't tell you the microfarads in which it's operating at. So although it's a fair test, it's not an accurate test. And with the cost of meters a lot more efficient now, you can get one that reads up to 200 microfarads easily for under $150 like I just talked about. Run capacitors are oil filled and they're silver, and they are tested the same way. Now these can be plus or minus 5 to 6% depending upon the manufacturer. Again, if the can is bulging, leaking fluid, or it's ruptured, of course it's failed. Don't trust it. Also remember, when you talk about capacitors, you have the microfarad readings, but you also notice you have a voltage reading. If you're consistently losing capacitors, check the voltage rating. If, for example, on that one there that's silver, 35 microfarad plus or minus 5% at 370 volts AC, if I keep losing it, I might then get one rated for 35 microfarad still. You got to keep it the same farad reading, but you can up the voltage. So get one that's rated for, say, 460. In doing so, you get one that's better constructed insulation-wise, and often that will help you keep from losing capacitors if you have voltage irregularity. The same can be true about the start capacitors. This one's rated for 86 microfarad at 270 volt. If I'm losing my start one consistently, maybe get one rated for 86 microfarad, but have it rated for maybe, again, 370 or 440. By upping the voltage, again, you improve your insulation class is what you're doing. Now, I mentioned about how you can discharge a capacitor, insulated screwdriver, run the points, or run the blade of the screwdriver across the points. It should discharge it. When in doubt, if you want to make sure, hook up your voltmeter to DC. Measure across the points. You should measure less than half a volt, knowing then it's full well, it's safe to handle. Okay. Now you have your capacitor in the back of a single phase motor. That then goes and energizes the motor through the switch, which is controlled by the governor. Basically, most centrifugal motors have this governor that when the motor hits about 2/3 speed, roughly about 2,500 RPM, it's going to swing out and disengage the start capacitor. So that's why I tell you the start capacitor is only a momentary unit. It's basically like the starter in your engine. It's designed to kick the rotor into moving and jump it, and then it will continue to spin after that. Okay. So then when the motor stops, the weight then is allowed to retract because you see there's springs coiled there. They'll pull that back, pushing up and engaging again the start capacitor, waiting for the next chance it needs to start. Your next item is you're going to have some sort of overload protection. And this is often built into single-phase motors. With three-phase motors, you often have to have that as a separate item. They might be called a thermal overload protection. They may be called heaters, overloads. There's many different terms for them. But the key is with a three-phase motor, you definitely need to buy a separate thermal protection. Now, in single-phase, don't always assume when you get to 3 and 5 horsepower, some of those do not have built-in thermal protection. You still might have to add it as a separate item, so be cautious there. Okay. Now, how this works is, remember the yellow wire coming from my start capacitor? That's there, and that's hooked up to a heating coil. Okay. Now, you have a piece of bimetal in there. It's a little piece. So you have your heating coils, and you have this little bimetal piece. And by bimetal, I mean it's two different metals. That one side of the metal is rigid at less than 140 degrees and keeps the unit touching, the points contacting. The other side is heat sensitive. And when the heat gets over about, you start to heat up, and when the heat gets over about 140, the secondary piece of metal becomes rigid and disengages the points. So now the motor is not seeing any current and will not start or run. You let it cool and it will automatically reset. Okay. A little bit now when you're doing testing is done from 1 to 2 and from 2 to 3. And you want to see continuity there, very low resistance. Yeah, okay, you don't want to see, basically if you're looking at an analog meter, you want it to swing to the left all the way, ideally. Okay, what you're measuring is from 1 to 2 is that disc, that bimetal piece that's now touching, allowing current to pass. When it's cool and the metal that is rigid at less than 140 degrees, it should be passing voltage. You want to see basically zero or very low resistance. 2 to 3 is the heat coil. You want to make sure that's there. That should always measure very low resistance. You want to make sure it's there. If you're measuring high numbers, or worse yet, the needle, or on a digital meter it says OL, which means out of limit, that tells you you've lost your heat coil. Okay. So again, when you heat it up, that piece becomes rigid at the other side becomes rigid and pulls the points out, and so you lose contact between 1 and 2. 2 and 3 should always have contact. Real quick word of caution, when you're dealing with an A.O. Smith motor, there's our voltage change device. Right there at the 230 mark, you'll see there's another little spade there with a hole in the center. If you're doing live voltage testing, remember that stays hot, so don't rest your hand on there. You can get shocked, so do be careful. There is the back of the motor complete. To the left, you see the start capacitor. At the 12 o'clock position, you have your thermal overload. Working your way around to the 3 o'clock position is your L1, L2 connections and your voltage change device. And dead center there is your starting points. Okay. Single-phase motors, you know, it looks intimidating when you look at the back, but they're fairly simple creatures to work with. Your start capacitor, like I say, if it doesn't work, the motor's not going to start. If the unit doesn't see any voltage, is it the thermal overload? So there's some basic things that you can troubleshoot very easily. We went over these in more detail in the basics motor testing course I gave. So I'm not going to go into a whole lot more detail now. You can always review that with the other episode. Let's talk about three-phase motors now. Here's the heart of our discussion. Three-phase motors, I want you to understand, is like a 3-piston engine. It always has the 3 lines coming in. And if they're balanced properly, they should be good, well and in phase, meaning that at any point, all three should equal out to zero on the measurement, so to speak. They should all zero out. And we'll talk about that a little bit later. What we're also like about three-phase is that you don't need a start capacitor. You also have 3 live legs pulling amperage, which means lower amp load. Best way I describe it is if you look at a merry-go-round, if you remember back when you were a kid, if you were the last one out, you had to push. So one person was pushing. If one of your friends felt bad for you, or maybe another one came late, then 2 people would be pushing, and you'd probably stand on opposite sides of the merry-go-round. With three-phase, you now have a third person with each of you equally spaced 1/3 of the way around and pushing in unison, 1, 2, 3, pushing on that merry-go-round. And with 3 people, you could even get it to go faster with less effort. That's essentially what we're doing with three-phase. We have 3 live legs or a 3-cylinder engine now pushing that armature, and it can do so at a lower amp load. And remember, amps equal heat. That's why a lot of people like three-phase. When you look at a three-phase, it consists of 3 coils, often designated the U, V, and the W. They're 120 degrees offset. Now this is a 4-pole motor we're looking at here. Now they also may be of the 3, the 6, the 9, or the 12 wire variety. But let me tell you, they're all 12 wire. And I know a lot of people say, oh, I've never seen a 12 wire sticking out of a motor. And you probably will not ever. Because the motor manufacturer puts wires 10, 11, 12 together internal to the motor. The other external wires is what you'll see to wire up. Now the other thing to remember is that these are often dual voltage. Some are even tri-voltage, but they're either high volt or low volt, or 230 versus 460, and the wiring will determine that. When you are ready to wire them up, you follow the manufacturer's instructions, and one of the first things we want you to do when you wire up a motor, the very first thing I would ask you to do is balance your leads. And in what we're doing is we're trying to find the proper wire connections to the motor. And remember, the motor windings, even though they're manufactured by the same manufacturer, windings can vary from motor to motor. Just like power coming in from the power plant can vary, especially if it's a Y delta versus a true three-phase, 3-pot system. Now, to explain what that is real quick, when you're talking about three-phase, ideally you'll have 3 hot legs coming into the transformer, and from the transformer 3 hot legs coming into the facility where it's distributed to the motor. Now, power companies, although they're a government-controlled monopoly and are supposed to be non-profit, so to speak, they make profits. Don't let them fool you. And so one of the things they do is they often do what's referred to as a Y delta, which is 2 live legs coming into 2, and granted they are oversized transformers or pots. And what they do is L1 comes from pot 1, L3 comes from pot 2, and leg 2 is a combination of stealing from pot 1 and pot 2 and balancing it in such a way to make a third leg. So these can cause issues with motors. If you're not doing this, testing the motors, rolling the leads, what we're going to show you here and explain, you can have issue. Now, you go into your starting mechanism, L1, L2, L3 will not shift. But what you're going to do is you're going to hook up T1, T2, T3. In the first example to the left, T1 goes to L1, T2 to L2, T3 to L3. You then test run it, taking amp measurements on each leg and record them. And then we'll talk here how we're going to do some math. But then we want to test it again. The reason we're doing this is we're trying to find the best winding combination to the best power incoming amperage. So what we literally do is take T1 where it was originally and move it to L2. T2 goes to L3 and T3 goes to L1. Then we'll take the amp measurements. Then we'll roll T1 now to L3, T2 to L1, and T3 to L2, and again take the amp measurements. Okay? The reason we're doing this is that we want to get these measurements and measure them and do some math here. Now, before we get into it, though, too, I just also want to warn you, remember, it's a live test. So do be careful and make sure you're using a proper amp meter. Amp meter has a clamp on. So it goes over the insulated wire. So even though you are handling a quote live wire, it will be that you're using the insulated portion. Now, if you have the opportunity, you can coil the wire 2 or 3 times and then put it in the amp meter. That helps give you a better amp reading. Where, for example, if you coil it 3 times, and you get an amp reading of 9, you divide it by 3 for the number of coils, and that would tell you it's 3 amp average. A lot of electricians I've talked to like to do that. In our industry, especially with larger wire gauge, it's not possible. So I understand that. Now, an analog meters also, especially if you're worried about that wild leg, remember analog meters show the variance better. Okay. Now, getting back to our math, as we show here, arrangement 1, we measured an amp load. L1 to T1 was 17 amps. T2 measured 15.3, and T3 measured 17.7. We totaled them up, and it was 50 amps total. We divide it by 3 because there's 3 legs there. So take the 50 divided by 3, and each leg should average 16.7. Okay. Then you take the actual measurement divided by the 16.7, and that gives you a variance. So the deviation for L1 was 0.3, the deviation for 2 was 1.4, deviation for 3 was 1.1. Now we look at then the largest deviation, which is the 1.4, and divide it by 16.7, which was the average we expected, and we get an imbalance percentage of 8.4. Okay, which is a fairly large number. Ideally, you want to see it as low as possible. Ideally, less than 2, but very rarely will you get that good of measurement. So then in arrangement 2, now remember in arrangement 2, T1 went to L2, T2 went to L3, and T3 went to L1. So when we measure that amp load, we got 16.7, 16.3, and 17. Again, a total of 50. Divided by 3, again, was an average of 16.7. But if you notice when we did the variance percentage, we took the 16.7 divided by 16.7, it was 0. 16.3 divided by 16.7 was 0.4. You'll notice in this case, the lowest number was, or the highest number was 0.4. Divided it by our average of 16.7, and it showed a deviation of 2.4. Arrangement 3, we did the same thing. We did all of our math, and we see that we came up with a variance of 4.2. What we found out by doing this is that your best arrangement was arrangement number 2, which is L1 to T3, L2 to T1, and L3 to T2. So that's how we would wire the motor and leave it. Now, the other thing I want to point out, and a lot of people overlook this, when there's an electrical event, a large storm rolls through, the transformer fails, something happens, you might want to go back to the place you're servicing and check these numbers again, because you might have to change the position of the wiring, especially if the transformers have to be changed out for any reason, because the balance would change. Now, a lot of guys ask me, what are you talking about? I said, well, have service contracts. If you're looking for ways to help generate revenue for your company, having a service contract for a dairy, for example, where you go out once a year and you do this test, or you're on call where it happens, you know there's a storm, or the farmer tells you, hey, I got a new transformer, you want to get out there and do this test, okay? Protect yourself. Protect the investment of the pump. A lot of people forget customers love it when you're proactive, not reactive, okay? So think about that. Again, to describe it, this is what a true three-phase here is on the left. That's a true delta. T1 has its own pot, T2 and T3 each have their own pot, or each has their own transformer. When you're talking Y delta, T1 has a pot, T3 has its own pot or transformer, but T2 is a combination of the two trying to mimic a third leg. And that's where you often have issues in balancing that you may not ever see really low variance. You just look for the best possible in the situation. The other thing to look at is also understand your amp load. Submersible motors will often give you a service factor amps, but above ground motors, if you want to know what the service factor amps are, you need to take the amp load, which is 2.3 or 1.15. Now, and it depends upon which voltage you're running, 230 versus 460. But either one of them, you multiply it by the service factor. So 2.3 times 1.3 is going to give you 2.99 service factor amps. So if you're worried about the motor pulling high load, for example, you're measuring 2.7, the max load amps is 2.3, remember you need to calculate in your service factor amps. Now, all companies, all pump companies go into the service factor. It's not uncommon. I'm not just saying stay right or Berkeley. I'm talking about across the whole industry. We're going to load that motor up as much as we can. Okay? Don't be overly concerned. Just make sure you do the math right to see that you're not. If you're pulling 3.2 amps and you shouldn't be higher than 2.99, that's cause for concern. Now, if you're going to do voltage testing, always be very cautious. Always wear your PPE. I'm sorry, there's an extra P there. But always use your personal protective equipment. Set your meter to the highest setting. If your meter has a 600 volt setting, you're sure it's only 230 volt. I always set it for the 600 volt because 600 volt versus setting it for, say, 300 volt just moves the decimal point. But if you put in higher voltage than the meter's expecting, it could cause damage to the meter, and it could also pass current to you if the meter is not well insulated. So always be cautious that way. In fact, my other piece of advice is use alligator clips to keep your hands free, and don't hold the meter while you're testing. Most meters have a kickstand or a hook mechanism where you can hang it or set it on the motor or near the side, and not be handling it when you energize it to be sure you're safe. Remember also, analog, don't overlook analog. Digital meters often capture a number and hold it, where an analog meter, the needle is always fluctuating. So if you're trying to trace down that wild leg, if you have an analog meter, it's going to reflex and move, showing you the variance and help you identify that leg quicker. Now, the other thing is that you have to be cautious of voltage drop. Reasons for voltage drop: well, one is a Y delta, and you didn't properly find the best combination for your wire connections that we talked about earlier. It could also be improper loading of the system. Dairies, for example, farms, they often have one junction box with a lot of equipment running off that one box. Wire size and breaker size can be a big issue. Always read the factory manual, okay? Another reference, if you're looking for wire sizing and such, I use a book called Ugly's Electrical Reference. It's often available at different bookstores, of course, Amazon.com. If you're familiar with electrical, Ugly's is a very nice little reference book. When in doubt, get help. Remember this: our license is typically only Cat 2 when it comes to electrical, which means we should only be going up to the pump control. If you have bigger electrical issues, there is no shame and there's no harm or foul in calling an electrician to help you. So ask for help when you need it. Controls: typically when you're talking about a three-phase motor, you're going to be using a mag starter, pump relay, or some sort of device that will be energized by a control, be it a pressure switch or a timer, and will pull the points in, sending the current down to the pump and energizing all three legs equally. You'll also probably have, like we recommended, some sort of heater or thermal overload that when they get hot, the points will contract, releasing the power and saving the motor, protecting it. All of these will be rated for some sort of class. Might be by voltage, by amp, or by both. In this case, this unit here is rated for 240, 30 full load amps. Now, remember, you got to calculate your service factor amps on the motor to make sure they fall within range here. They might also tell you horsepower, single phase versus three phase. Line rush, LRA is line rush amps, which means your in-rush current or in-rush amp load. Typically, as long as you pay attention to the full load amps and size it that way, you should be covered. When you're looking at these units for testing, okay, if you test the incoming point to the exterior point when the unit is off and the mag relay is not energized, you should see OL or open. You should see the needle on the analog stay all the way to the left. You shouldn't see it moving because you don't want it passing voltage at this time. Then you can often push down on the center there, push down, make the points contact. Again, of course, this will be with power off. Anytime you're testing with an ohm meter, make sure the power is off. So when you push down, then you should say 0, or ideally the analog meter should run to the right. This is at R times 1, and you want to see, basically 0 or very close to 0. Okay, so when you push that button, that's where you want to make contact, and you're mimicking it passing voltage. For overload, you can test from the incoming to the outgoing line, and you should measure 0. Ideally, it's passing voltage. The points are contacting. The analog meter should run to the right. Your digital meter should give you a very low number, 0, or maybe like a 0.5, but a very low number. Now that overload 2 often will have a mechanism where you can force the points apart, and we do so as to mimic a fault condition. Then the meter should swing all the way back to the left. Your digital meter should go to OL, which means out of limit, which means it's not seeing any connection. When you connect these, you can connect the relay via using the power coming in from the motor. So you got your L1 line coming in before you hook it up to your start relay, of course. You went on the live side, you'll pull your current off. You have your control, be it a pressure switch or whatever. When the pressure switch closes, for whatever reason it might close, demand, if you're using a pressure switch timer, it'll pass the current. The current will go into the coil, pull down on the magnet, and energize the pump. Remember, thermal overloads or heaters, when you're talking three-phase, are typically add-ons. You have to add them on. They're not going to be built into the motor typically. You can also pull line voltage in from a separate 115 source, for example, or maybe 24 volt source, depending upon the coil demand. Wired similarly, when the control device, be it a pressure switch or a timer, closes the relays, the voltage is passed, the coil sees the energy, pulls down and passes voltage to the motor and starts it. Okay. Also note that a lot of these units, even older ones like this old furnace, have sensitivity settings for the thermal overloads, so you can adjust them. If you're in a room that has ambient high temperature, you might make it a little less sensitive, or vice versa. If you want to protect the equipment quicker, ensure you don't damage it, make it more sensitive. So depending upon the manufacturer, and again it comes back to reading the factory manual, find out how you set that, because often they are adjustable. Measuring the windings, when you're talking three-phase, the first answer is, no matter what winding you're measuring, T1 to T2, T2 to T3, T3 to T1, they should all measure relatively the same. In this example, we're measuring 11.1, 11.1, and 11.2. Would I be overly concerned if I'm measuring 11.2 compared to 11.1? No. It's a tenth of an ohm. So it could be the wire nut that you see there holding some of the wires together. It could be how the meter was clamped in particular. There's various reasons why you might not get the exact same measurement, but they should be very close. That's your first test. If you ever single phase a motor, and I'll explain what single phasing means, is that a motor is very dedicated. I always kind of compare it to my old faithful dog, Carmel, who's my hunting dog, where Carmel wants to make sure I'm happy, and she'll do whatever it takes out there in the field. She would run herself to death if I let her chasing rabbits. But of course I wouldn't let her do that. I don't want Carmel to get hurt. Your electric motor is the same way. And if you don't put good thermal protection on it, what can often happen is one leg gets weak or drops out. Say, for example, in that Y delta, that one line that's connected to pot 1 and pot 2 trying to make up a third leg, it might drop off, or it might just be completely out of sync. And what happens is then the winding 1 and winding 3 try to pick up extra amp load to make up for the work difference. And they'll get to the point where they get so hot if you don't have thermal protection that they flash, they burn. And if you know, all motors run on blue smoke. You let the blue smoke out, the motor's done. Now, that's a joke, but it really is true. All motors run on smoke. Once that motor goes poof, it's done. And when you take the motor apart, what will happen is you'll see 2 windings that are burnt up and 1 single phase winding that's perfectly fine. So that's where it gets the nickname single phasing. So when you measure that, you might get, for example, 297 on L1 to L2. L2 to L3 measures 11, and L3 to L1 measures 132 ohms. That tells me you single phase the motor. You have 1 decent reading because you're reading the good winding, and the rest of them are shot. Okay. Now, when in doubt, like I say, the first and foremost, make sure the power is off whenever you're doing any ohms testing. And ideally, all of the windings should read the same. If you want to see if they're within spec, always refer to the factory manual. All motor manufacturers are going to give you numbers for what they want to see in when you're measuring the windings. Okay. Insulation checks. When you're checking insulation, I highly recommend a meg ohm meter, a megger. And what a meg ohm meter does is it sends voltage down into the insulated wire, trying to get it to go to ground at high voltage. Often, as you see here, we have it set for 1000 volts, and we're measuring 2 or greater gigaohms. So I know that motor insulation is fine. So as you see here, I have the red wire hooked up to one particular winding, and the black round wire hooked up to the motor, because I'm trying to make sure the motor is safe. Whenever you do an insulation test, the bigger the number, the better. Okay, depending upon the manufacturer, and a lot of people, well, how do meg ohm meters work? Well, like I say, what we're doing is we're sending down high voltage, higher than what a normal Simpson meter, for example, would put down. They put them in the range of all the way up to 1000 volts DC. Often, depending upon the manufacturer, they might have special settings where the test probes can only go in a particular way to test for meg ohm meter testing. Fluke here, for example, they also color code. Some of them have added features where, for example, you have the alligator clip, and then you also have the probe, and you have a test button that's on the probe. These are handy features, I won't deny it, but it's also costly. Now, I'm going to be blunt. Last year, I had a fluke walk out the door on me. I lost it. And there's nothing worse than having to go back to your boss and say, oh, a $1,000 meter walked out the door. My boss challenged me to find a more economical, and they're out there, believe me. This meter here, I'll tell you freely, I got it off of an online service, Amazon, about $150. But you'll notice in this one, there's less color coding, and you have to read the owner's manual. So the one thing about meg ohm meters is a lot of guys are nervous using them. I teach meter classes all over the country. The best advice I have is, 1, read the factory owner's manual. 2, play with them, get used to them, and start using these meters. And typically, when you're talking megometer, don't be handling the probes, because when you push the test button, there is voltage live there. So be careful that way, but play with them and start to test motors that you have. I'm sure you have a dead motor in your shop, so let's go ahead and pull that motor out and start playing and testing in it and see how we can get these measurements to work more accurately. The best way to become more familiar with the meter is to use it. Okay. So in this case, you'll notice I have to hook up the wires on the two left probes. They're both red. It says test insulation. Okay, so I'd hook it up. Now, in this case, here's the good old analog. And I know some guys say, well, you just can't find analog meters anymore. Again, I'll tell you, man, it's not that hard. I found this one in 2 minutes, and good old Amazon. But there's other ones out there. There's other companies out there that have websites, Home Depots, Lowe's. These are found. You might not find them always when you walk in the store, but a lot of these higher dollar meters are available online and can be shipped to the store for you. Now in this case here, I have it set up. I'm measuring that same motor. You don't show the motor hooked up, but I'm showing you the line is the red, the earth is the black probe set. I set my insulation test to 500 volts DC. I push my button, and you'll notice the needle doesn't even move. It's all the way to the left. It's out of limit again. Knowing that on my primary test with the digital, it measured greater than 2 gigaohms, I'm not surprised that little needle is all the way to the left and didn't even budge, because that's a brand new motor, never even been tested. Okay, so meg ohm measurements, what we're doing, and when you set it up, remember, I typically go right to 1,000 volts because you're typically working with 460 volt. If you're working with 230 volt, you can set it to 500. So you set your insulating voltage up to where you want it, either 500 or 1,000. You push the test button, and this is called a spot test. The needle will swing and will give you a measurement. As we're looking here at this one, if that needle were to have swung to, say, the number 5 on the black scale, that would have been 5 million ohms, which, depending upon the motor manufacturer, is probably fine. When you're measuring any insulation test for a motor, always refer to the factory owner's manual. When you're talking submersibles, they often allow you lower numbers because the motor is down in a grounded water supply. Whereas an above ground motor, it's not typical that above ground motor, like say for example Beldor, they want to see 5 million ohms or better, or they're concerned the motor might become hazardous to those around the motor. So always refer to the factory owner's manual when you're looking for those resistant numbers. Spot test versus DAR or pi test. Now this is really talking above ground pumps. When you look at below ground pumps, you're also measuring wire condition, and it can be more difficult. But this is something I mentioned to people, in that most of the tests we do are spot tests, meaning that we test the insulation, we push the button for a moment, we get a number, and we move on. DAR and pi testing, which often your meter, depending upon it, has an auto function like the flukes and such. Even this Mastech here, you can set it up and it will automatically do it. And why that's convenient is for this reason. The DAR test is a 1 minute test, and the pi test is a 10-minute test. And the difference between the two is there's the dielectric absorption rate, that's the DAR test, and then there's the polarization index test. And what we're doing is we hit our test, and we're looking for it to run, and we're looking for a ratio. So, for example, with the DAR test, where it's looking at the 30-second and the 60-second rating number, and it's going to compare the two, and it wants to see a differential. By running voltage into the wire, it allows the electrons to better organize themselves and line up and have more ease of effort to leave the wire insulation proper. So the longer you run it, the higher the chances you can detect these issues. I know, for example, elevator repairmen, escalators, a really good example is actually your amusement parks. They often test these motors because they're using variable frequency drives, And especially with the amusement park, think about it. How many lives are counting on that motor running properly each and every time? Now, what you then do is you get these numbers, and like I say, it will do the test for you automatically. You set your voltage, it runs, it gives you the time, and it will give you the ratio. You can then plot it. And if you look at the spot versus pi testing, spot testing, it's not uncommon to see rapid jumps or even to see sometimes improvements, so to speak, depending upon how the meter is hooked up, depending upon different situations, depending upon motor condition. So for example, with a spot test, you might, on first installation of motor, be measuring that 2.0 giga-ohms, or in this case, they're measuring about 15 million ohms. Then you see a sudden drop-off. Reason for that is once the motor starts to see work, the insulation becomes conditioned. So there isn't surprise there's a rapid drop-off. Pi testing, you don't see much of a rapid drop-off. But as you look at it, a lot of times, again, this harkens back to what are you doing for your customer in efforts to help be of service to him. You know, in this case here, if you're watching it, if the motor is still running, but it's on the pi test and even on the spot test, it's obviously on the downswing. The insulation is degrading. You give that customer the information. Let him make the decision. Especially when you're talking, like, for example, a dairy or a chicken farm, for example. And chicken farmers are very concerned because, in my understanding, in 3 hours, if they don't have water, chickens can start to die. So if you can give them better information and start saying, hey, this will help possibly clue us into when that motor is going to fail or potential failure, this is information customers want to hear. Now, granted, this does not, there's no way you can predict a lightning strike, a power surge, something like that happening. But this would tell you how the motor is running and, more importantly, how the insulation is degrading to give you a little bit more of an insight. So the more informative you can be to your customers, sometimes the more help you are. And that often builds very good relationships with customers. You know, the most important thing about any of us, including me as a trainer, is the relationships we build. And I'm hoping that we give you good information that's value, that you keep coming back to us, okay? I want to thank you for your time. Remember, any of these webinars are always works in progress. I'll be honest, you know, these will evolve over time as different information comes in from the factory and from the field. So your input is very important. A lot of these are webinars I do because they're asked for. If you have any insights, give us a shout out at training.institute@pentair.com. Otherwise, have a great day. Thank you for listening, and take care.